1687. Isaac Newton publishes Principia Mathematica. 1 equation. Gravity falls off as 1 over r squared. The inverse square law. Simple, elegant, and powerful enough to predict planetary motion for 3 centuries. 1905. Albert Einstein publishes Special Relativity. Revolutionary, but incomplete. Gravity doesn't fit. (1907). Einstein, still working at the patent office, has what he'll later call the happiest thought of my life. A person falling from a roof feels weightless. They can't tell they're in a gravitational field. And a person in an accelerating rocket in deep space feels weight, identical to gravity. The equivalence principle. Locally, you cannot distinguish between gravity and acceleration. Einstein realizes, if gravity and acceleration are equivalent, and acceleration curves trajectories in spacetime, then gravity must curve spacetime itself. But having the insight and proving it mathematically? 2 different problems. 1908 to 1911. Einstein tries to formulate his theory using ordinary calculus. It doesn't work. The math isn't powerful enough. He needs something more sophisticated. 1912. Einstein reconnects with Marcel Grossmann, a mathematician who'd shared notes with him during university when Einstein skipped lectures. Grossmann introduces Einstein to tensor calculus and Riemannian geometry, the mathematics of curved spaces developed 50 years earlier by Bernhard Riemann. Einstein later admits, "I have become imbued with great respect for mathematics, whose more subtle parts I considered until now, in my ignorance, as pure luxury." 1913. Einstein and Grossmann publish the Entwurf, outline theory. It's close, very close, but not quite right. The equations aren't generally covariant. They don't have the same form in all coordinate systems. They depend on how you choose to measure things. Einstein knows this is wrong. Physical laws shouldn't depend on arbitrary human choices of coordinates, but he can't fix it. 1914. World War I begins. Einstein moves to Berlin. His marriage is falling apart. Europe is tearing itself apart, and he's stuck on these equations. Meanwhile, mathematician David Hilbert in Göttingen is also working on the problem. He has Einstein's 1913 paper. He's making progress. Einstein realizes he's in a race. Not with an enemy, with a colleague, but a race nonetheless. November 1915. 4 Thursdays, 4 presentations to the Prussian Academy. Einstein is revising his theory in real time, presenting new equations each week. November 4th. Einstein presents modified field equations. Better than 1913, but still not quite right. November 11th. He corrects a mistake. New equations. Getting closer. Between presentations, Einstein applies his equations to Mercury's orbit, the anomaly that had puzzled astronomers for decades. The equations predict 43 arcseconds per century of perihelion precession, exactly what's observed. Einstein writes to a friend, "I was beside myself with joyous excitement. The result of Mercury's perihelion motion, how it turns out right to a precision of seconds of arc." November 18th. He presents the Mercury calculation to the Academy. First experimental success. November 25th. Einstein presents the final correct field equations. R mu nu minus 1/2 Rg mu nu plus Lg mu nu equals, open parenthesis, 8 pi g over c to the 4th power, close parenthesis, t mu nu. 10 years. From elevator thought experiment to these equations. The most beautiful theory in physics. Einstein later describes these weeks as the most intense intellectual experience of his life. He's 36 years old. And 110 years later, physicists discovered something Einstein never knew was hidden in those equations. Something that would have astonished him. Newton's law worked well enough to navigate ships and predict eclipses, but it failed on Mercury. Einstein's equations worked perfectly. 1919, Arthur Eddington measures starlight bending around the sun during a total eclipse. Newton predicted 0.87 arcseconds. Einstein, 1.75. Observation, 1.75. Einstein becomes a global celebrity overnight. Lights all askew in the heavens. Einstein theory triumphs. But general relativity is hard. Ricci curvature tensor, 10 components. R, scalar curvature. Metric tensor, geometry of spacetime. Lambda, cosmological constant. Einstein added, removed, then it came back. G, Newton's gravitational constant. C, speed of light. T mu, stress energy tensor, matter and energy. 10 coupled, nonlinear, partial differential equations. A century later, graduate students still struggle with these equations. Solving them for realistic situations requires supercomputers. From Newton's single equation to Einstein's 10 equations. From elegant simplicity to profound complexity. But what if that complexity is hiding a deeper simplicity? 1960s. Physicist Joseph Weber builds the first gravitational wave detector, a massive aluminum bar that should ring like a bell when a gravitational wave passes. He claims detection. The physics community is skeptical. Other groups can't reproduce his results. Weber was probably detecting noise, not gravitational waves. But he proved something important. You could try. 1972. Rainer Weiss at MIT proposes a different approach. Laser interferometry. Send laser beams down 2 perpendicular arms, several kilometers long. Bounce them off mirrors. Recombine them. If a gravitational wave passes, it stretches one arm and compresses the other. The laser beams go out of phase. You see interference fringes shift. The stretching? In a 4-kilometer arm, a gravitational wave from merging black holes stretches space by about 10 to the minus 18 meters. That's 1/10,000th the diameter of a proton. That's like measuring the distance to the nearest star to within the width of a human hair. Engineers say it's impossible. But Rainer Weiss, Kip Thorne at Caltech, and Ronald Drever form a collaboration. 1990s. They convinced the National Science Foundation to fund it. $300 million initially. Eventually, over $1 billion. 2 detectors. One in Hanford, Washington, one in Livingston, Louisiana. 1,865 miles apart. 8 years of construction. 2002 to 2010. Initial LIGO runs. Hundreds of millions of dollars. Years of data collection. 0 detections. Critics call it a waste of taxpayer money. Some physicists wonder if gravitational waves even exist. 2010 to 2015. Advanced LIGO upgrade. More sensitive laser. better isolation from seismic noise, improved mirrors. The sensitivity increases tenfold. September 14th, 2015, 3:45 a.m. Central Time. A signal arrives at Livingston. 7 milliseconds later, the same signal at Hanford. A chirp, rising in frequency and amplitude, lasting 0.2 seconds. The on-call scientists see it immediately. It's loud, unmistakable. But wait. Advanced LIGO isn't supposed to be operational yet. They're still doing engineering runs. Is this real? Or is it an injection test? Fake signals the team injects to keep analysts sharp. Days of checking. It's not an injection. The hardware team didn't inject anything. It's real. September, February, 5 months of verification. Checking everything. Ruling out every possible source of error. Could it be an earthquake? No, different waveform, and both sides saw identical signal. Could it be electromagnetic interference? No, the defendants are shielded. Could it be a cosmic ray? No, wrong signature. Could it be a conspiracy? They check who had access to the data at 3:50 a.m. No one who would inject a fake. They match the waveform to General Relativity predictions. 2 black holes, 29 and 36 solar masses, 1.3 billion light-years away, spiraling together at half the speed of light, merging, radiating 3 solar masses of energy as gravitational waves in 0.2 seconds. More power than all stars in the observable universe combined for that fraction of a second. February 11th, 2016. The press conference. David Reitzer, LIGO director. Ladies and gentlemen, we have detected gravitational waves. We did it. The room erupts. Journalists, scientists, everyone on their feet. Kip Thorne is crying. 40 years of work. It worked. Since then, a flood of detections. Over 300 black hole mergers, neutron star mergers. Every 3 days now, another detection. July 2025. GW2 31123, the most massive black hole merger ever observed. 2 black holes, 100 and 140 solar masses, creating a 225 solar mass remnant. January 2025. GW2 50114, the clearest signal ever recorded. Signal-to-noise ratio of 80, nearly triple the clarity of GW 150914. So clear, they detected the first overtone of the Kerr solution, the ring down of the final black hole settling into equilibrium. Einstein's equations predicted it exactly. September 2025. With 300+ merger detections, physicists have unprecedented data on extreme gravity. And 3 researchers at Caltech, Jiaxi Wu, Siddharth Boyeneni, Elias Most, noticed something. The waveforms follow a pattern. Not just any pattern. They behave as if gravity works like electromagnetism. Let's understand what they discovered. Maxwell's equations describe electromagnetism. 4 equations relating electric field E and magnetic field B. An electric charge creates an electric field radiating outward. The field strength falls as 1/r². Move that charge and you create a magnetic field circulating around the current. Accelerate the charge and electric and magnetic fields leapfrog through space, an electromagnetic wave. Now, gravitoelectromagnetism. Replace electric field E with gravitoelectric field E sub G. replace magnetic field B with gravitomagnetic field B sub G. A mass creates gravitoelectric field, what we normally call gravity. Field strength, 1 over r squared. Move that mass, you create a gravitomagnetic field. Frame dragging, the effect where rotating masses drag spacetime around them. Accelerate the mass, like black holes spiraling, and you get gravitational waves, gravitoelectric and gravitomagnetic fields leapfrogging through spacetime. The mathematical structure is identical. But here's the profound part. This isn't an approximation. This isn't a close enough analogy. Wu, Boyeneni, and Most took Einstein's full, exact field equations and reformulated them. Step 1. Choose specific coordinates adapted to the symmetry of the spacetime. Step 2. Define gravitoelectric and gravitomagnetic fields from the metric Tesson components. Step 3. Rewrite Einstein's equations in terms of these fields. And out comes equations that look exactly like Maxwell's equations. With one critical property, the inverse square law. Not just in weak gravity, far from masses, that's been known for a century. In strong gravity, near black hole horizons, during mergers. Elias Most. This is a very non-trivial insight. Alexander Filipov, University of Maryland. Very nice. There is novelty in the interpretation of results from fully non-linear general relativistic simulations in terms of effective electromagnetic fields. Why does this work? Geometry. In three-dimensional space, field lines from a point source spread uniformly. Surface area of a sphere, 4 pi r squared. So field strength per unit area falls as 1 over r squared. Pure geometry. Einstein curved spacetime. But for spherically symmetric systems, like non-rotating black holes or the average field from spinning ones, the spherical symmetry persists. Birkhoff's theorem, 1923. Outside any spherically symmetric mass, the vacuum solution is unique, the Schwarzschild metric. And in that geometry, field lines still spread as 1 over r squared. Newton's inverse square law isn't replaced by Einstein. It's encoded in the geometry of curved spacetime. 3 descriptions of gravity. Layer 1, Newton 1687. Force. Layer 2, Einstein 1915. Curved spacetime. Layer 3, Wu, Boyeneni, Most 2025. Gravitoelectric, gravitomagnetic fields with 1 over r squared symmetry. Mathematically equivalent. 3 faces of the same reality. 1918. Mathematician Emmy Noether proves every symmetry corresponds to a conservation law. Time symmetry, energy conservation, space symmetry, momentum conservation, rotation symmetry, angular momentum conservation. Symmetries are fundamental to physics. The Caltech reformulation reveals a symmetry hidden in Einstein's equations for 110 years. Inverse square behavior isn't approximate. It's a symmetry property of curved space-time. There's precedent. 1865. James Clerk Maxwell unifies electricity and magnetism, but his equations looked strange, asymmetric, not obviously connected to mechanics. 1905. Einstein discovers Maxwell's equations contain hidden Lorentz symmetry, the symmetry of special relativity. The equations were pointing to space-time unification. Now, 120 years later, Einstein's equations contain hidden structure too. What is this symmetry pointing toward? Layer 4? Some think gravity emerges from quantum information. from entanglement, from holography. The inverse square symmetry might be the clue. Einstein's theory made predictions. Physicists spent a century testing them. 1919, starlight bending. Arthur Eddington travels to Principe Island off Africa for total solar eclipse. Photographs stars near the sun's edge. Result: stars appear shifted by 1.75 arc-seconds. Exactly Einstein's prediction. Newton predicted 0.87 arc-seconds. Wrong. Einstein predicted 1.75. Correct. 1959. Gravitational redshift. Pound and Rebka at Harvard use Mossbauer effect to measure gamma rays traveling up a 22.5-meter tower. Gravity slows time. Photons climbing lose energy. Redshift. Measured redshift matches Einstein to 1% accuracy. 1974. Binary pulsar. Hulse and Taylor discover binary pulsar, two neutron stars orbiting each other every 8 hours. Einstein predicts they radiate gravitational waves, losing energy. Orbit should shrink. Measured orbital decay over 30 years. Perfect match to Einstein's prediction. This is the first indirect evidence for gravitational waves. Nobel Prize, 1993. 1980s. GPS satellites. GPS satellites orbit at 20,000 kilometers altitude. Clocks run faster, weaker gravity, special relativity effect, and slower, orbital velocity, general relativity effect. Without relativistic corrections, GPS position errors accumulate at 10 kilometers per day. With corrections, accurate to meters. Relativity in your pocket. 2004 to 2011. Gravity Probe B. NASA launches satellite with 4 ultra-precise gyroscopes. Orbits Earth for a year, measures frame dragging, how Earth's rotation drags spacetime around it. Einstein predicts 39 milliarc-seconds per year of precession. Measured, 37 plus or minus 7 milliarc-seconds. Match within error. Wow. 2015 to 2025. Gravitational waves. 300 plus black hole mergers detected. Every waveform matches Einstein's predictions. 2019. Black hole shadow. Event Horizon Telescope images M87's black hole. Shadow size, 42 microarc-seconds. Einstein's equations predict shadow size from mass and distance. Perfect match. 2020 to 2025. Gravitational wave background. Pulsar timing arrays detect gravitational wave background from thousands of supermassive black hole mergers across cosmic history. Another Einstein prediction confirmed. A century of tests. Weak fields, strong fields, slow motion, high speed, small scale, cosmic scale. Every test, Einstein wins! And in every test, in the appropriate limit, Newton's inverse square law emerges. Not replaced, contained. The Caltech reformulation isn't just theoretical, it's practical. Teaching general relativity has been brutal. Tensor calculus, differential geometry, years of preparation. But if you can recast Einstein's equations as electromagnetic-type equations, which physicists already understand, GR becomes accessible. Alexander Filipov promises to provide valuable intuition for a broad class of problems involving compact object mergers. For LIGO, faster simulations, clearer physical intuition, better waveform templates. O5 observing run starts 2026. More mergers, more data, more tests of inverse square symmetry. But the biggest implication: quantum gravity. At 10 to the minus 35 meters, the Planck scale, both general relativity and quantum mechanics break down. We need a theory that unifies them. String theory. Replace particles with vibrating strings. Requires 10 or 11 dimensions. Gravity emerges from closed string loops. Mathematically beautiful, but untestable at current energies. No experimental evidence yet. Loop quantum gravity. Quantize space-time itself. Space becomes discrete at Planck scale, a network of quantum loops. Spin networks replace smooth space-time. Area and volume are quantized. More conservative, doesn't require extra dimensions, but harder to connect to particle physics. Holographic principle. Most radical idea. Gravity isn't fundamental, it emerges. 3D gravity is encoded in 2D quantum field theory on a boundary. ADS-CFT correspondence. Black hole entropy is proportional to surface area, not volume. Why? Because information is stored on the two-dimensional horizon, not in the three-dimensional interior. ER equals EPR conjecture. Maldacena and Susskind, 2013. Einstein-Rosen bridges, wormholes, and quantum entanglement are the same phenomenon. Geometry equals entanglement. If space-time emerges from entanglement, and Newton's inverse square law is encoded in space-time geometry, then maybe 1 over r squared emerges directly from quantum correlations. The Caltech reformulation hints at exactly this. If gravity in extreme conditions behaves like electromagnetism, if simple inverse square pattern persists everywhere, maybe both Newton and Einstein are emergent descriptions of something simpler underneath. There's precedent. 19th century, thermodynamics, temperature, pressure, entropy, phenomenological laws. 20th century, statistical mechanics. Temperature is just average molecular kinetic energy. Entropy is counting microstates. Complex thermodynamic laws emerged from simple atomic motion. Could gravity work the same way? Complex curved space-time emerging from simple quantum information? The inverse square symmetry might be the fingerprint of that deeper reality. 1960. Physicist Eugene Wigner writes about the unreasonable effectiveness of mathematics in the natural sciences. His puzzle: why does math work so well? Why are simple mathematical structures often correct? Newton's F equals ma, Maxwell's equations, Einstein's E equals mc squared, Schrödinger's equation, all elegantly simple. The inverse square law, one of the simplest possible relationships, and it's hiding in Einstein's tensors. Physicists trust aesthetic sense. Simple laws are often true laws. When theories make identical predictions, choose the simpler one. The Caltech reformulation simplifies general relativity without losing accuracy. Nature might be saying, look for the simplicity. Let's step back. Newton gave us gravity that works on human scales: planets, apples, cannonballs. Einstein gave us gravity that works everywhere. GPS satellites to black holes, solar system to cosmology. But at the smallest scales, 10 to the negative 35th meters, even Einstein breaks down. We need layer 4. 2020 research suggests space-time itself might be emergent, not fundamental, derived. Just like temperature emerges from molecules, space-time might emerge from quantum entanglement. Einstein-Rosen bridges, wormholes, equals Einstein-Podolsky-Rosen pairs, entanglement. Geometry equals entanglement. If space-time emerges from entanglement, and Newton's law is encoded in space-time geometry, then 1/r² might emerge directly from quantum correlations. Full circle. Quantum to Newton to Einstein to quantum. (1687). Newton discovers gravity falls as 1/r². 1915. Einstein shows gravity is curved space-time. 2025. Caltech physicists show Newton's law is hidden in Einstein's equations as a fundamental symmetry, not contradiction, not replacement. Layers. LIGO continues to listen. Every 3 days, another black hole merger, another test of general relativity, another confirmation of the inverse square symmetry. Next generation coming. Cosmic explorer with 40-kilometer arms. Einstein telescope underground. LISA in space, detecting supermassive black hole mergers. Each will probe gravity more precisely, test limits, search for deviations, and theorists continue searching for layer 4. The theory that explains why Newton is hidden in Einstein. The theory that shows what they're both approximations of. Here's the lesson physics teaches us. We don't replace old theories with new ones. We reveal layers. Newton wasn't wrong, he was incomplete. His theory works perfectly for everyday speeds and weak gravity. Einstein isn't wrong, he's incomplete. His theory works perfectly for all speeds and all gravitational strengths we can currently test. Layer 4, quantum gravity, will contain Einstein as a special case, just as Einstein contains Newton. Each theory nests inside the next. Each points towards something deeper. The inverse square symmetry discovered in September 2025 is a signpost. It says, simplicity hides in complexity, and complexity emerges from simplicity. The universe seems to operate on elegant principles. 1/r², symmetry, conservation laws. Even when we write them in complicated ways, tensors, differential geometry, the simplicity persists underneath. Einstein spent 10 years creating General Relativity, the most complex, beautiful theory of gravity ever conceived. And Newton's 400-year-old law was hiding inside it all along, not as a relic, not as an approximation we discard, as a fundamental symmetry, a clue about the structure of reality. The search continues. LIGO listens. Theorists calculate. Experiments probe. The universe operates at every scale. Quantum fluctuations, falling apples, colliding galaxies. And somehow, all these scales are connected, related through layers of description. We haven't found the final theory yet, but discoveries like the Caltech reformulation show we're getting closer. Closer to understanding why nature chose these particular laws. Why simple patterns, like 1/r², persist across theories separated by centuries. Why mathematical elegance seems to be a guide to truth. An apple falls. Newton gave us one explanation, a force pulling downward. Einstein gave us another, curved spacetime. Wu, Boyeneni, and Most gave us a third, gravitoelectric fields with inverse square symmetry. And layer 4, whatever it is, will give us the deepest explanation yet. Perhaps all three are different ways of describing how quantum information creates the illusion of gravity. Perhaps the apple falls because the universe is made of correlations. This is Cosmic Canvas, where we explore the layers of reality, from Newton's falling apple to Einstein's curved spacetime, to whatever lies beneath both. Until next time, keep searching for simplicity. The universe hides its deepest secrets in its most elegant patterns. And remember, every time you see something fall, you're witnessing 4 centuries of physics compressed into a moment. Newton's force, Einstein's curvature, Caltech's symmetry, and whatever layer 4 will teach us.